Hello, this is E637. I'm Charles Bouman, and today we're going to learn about the joy of multivariate Gaussian distributions. So we're going to start off. I'm going to just quickly review once again what a multivariate Gaussian distribution is. I mean, the beauty of the multivariate Gaussian distributions is they're a great way of describing to a first-order approximation the distributions of jointly dependent quantities in systems, and they're a fantastic application of linear algebra, and they really give insight into a lot of concepts of linear algebra that you can otherwise kind of learn in a kind of antiseptic way. But this kind of provides an intuition for understanding the concepts of linear algebra, particularly Eigen Decomposition and things like singular value decomposition. And in fact, you've done this in the lab, which I think is due to, this week? Oh, it's due already. Okay, so you already know it. So now, since you already know it, now you can learn it in greater depth by hearing the lecture. Okay? So here we go. So the multivariate Gaussian distribution is like this, right? This is the density function for a multivariate Gaussian. 1 over 2 pi p over 2, where p is the dimension. R is the covariance matrix, so this is the minus 1/2. And this is exponential of minus 1/2 x transpose R inverse x. So this is the random variables with this density is normal with, I should have put a mean in there, but that's mean 0 and variance covariance R. Okay, if I had replaced x here with x minus mu transpose R inverse x minus mu, then in that case it would be normal with mean mu and covariance R. Okay? We'll usually consider the zero mean case because it's simpler to work with, and generally most things that are true in the zero mean case, are easily generalized to the non-zero mean case. So the covariance matrix R, this is a symmetric and positive definite matrix, okay? And by positive symmetric means that R equals R transpose, that's symmetric, and positive definite means that for all x a member of R to the p, x transpose Rx is greater than 0. If it was positive semi-definite, then it would be greater than or equal to 0. But we'll assume it's positive definite, so that the density. If it's not positive definite, if it were positive semi-definite, then the integral of the density would be infinite. Because there would be some direction in which the density doesn't decay, and if you integrate it out far enough, you get an infinity. So we have to assume that it's positive definite for this to be well defined. Okay, so now what happens is that for any positive definite symmetric matrix R, you can find the Eigen Decomposition. So the Eigen Decomposition has the form E lambda E transpose, where so E, this is orthonormal. It's an orthonormal matrix. I'm assuming everything's real valued here. And lambda, this is diagonal. Okay? So here, E, by orthonormal, so orthonormal implies that E transpose E equals I. So for an orthonormal matrix, the transpose is the inverse. And E here is a matrix, and its columns, or we'll call E1 through EP, these columns are eigenvectors. And lambda here is a diagonal matrix. So you have lambda 1 through lambda p, and these are zeros. Okay? And lambda I, these are eigenvectors. Eigenvalues. Eigenvalues. Okay? So if you think about what this equation means, so if you have that R, hold on, let me do that way. Okay, let me start at the top, so I have more space. Okay, R here is equal to E lambda E transpose, right? So that means that R times E is equal to E times lambda times E transpose times E, right? But E transpose times E is I, right? So this is really just equal to E times lambda, right? Now if I expand that out, what does that mean? That means that what that means is that I have R times E1 through EP is equal to E1 times EP times this matrix, which is lambda 1 through lambda p, and there's zeros here, right? Well, when I take these and multiply them, I take this first column here, and I multiply it by this matrix, and then I'll get the first column out. So if I look at that, what I'm really saying is I'm saying that R times EK is equal to lambda k times EK. That's what this equation. This is just a matrix way of representing this result. So this is this is the eigenvalue and eigenvector. So this is the kth eigenvalue slash vector, right? So that's what this is. Okay, now, good. Okay, so let's see. So if I take x, okay, let me hold on this idea for a moment. If I take x, so x is distributed as normal with mean 0 and some covariance r, right? And if I take x and I say, well, x tilde equals a times x, right? Then what's the covariance of x tilde? Well, first of all, then this implies that the mean of x tilde is equal to the expected value of a times x, right? It's a times the expected value of x, so that's equal to 0 in this case. If it was mean mu, then it would be mu times a. Now, if the now the covariance r tilde, say, of x tilde then is equal to the expected value of x tilde times x tilde transpose, right? So just substituting in here, I get that this is equal to the expected value of ax times ax transpose, right? But that's equal to the expected value of ax times, whenever you transpose a product of matrices, and a vector is a special case of a matrix, right? What you do is you take the transpose of each element and then you reverse their order. So this becomes x transpose a transpose. Now A and A transpose are deterministic, so I can take them out of the expectation. So this, and it's also, the expectation is linear, so they're linear operators, so I can take them out. So this becomes A times R, A transpose. Okay. So that's a general result. Now, if in the particular case here, if I take x tilde to be equal to E transpose x, where this is the eigentransform, right? Then what happens is that R tilde here is going to be E transpose RE. So that's equal to E transpose, R here is, it's E lambda E transpose times E. So that's equal to E transpose E lambda E transpose E, and that whole thing is just lambda. So what this tells you is that if you take x and you transform it using the inverse transform of this matrix E, what you get is a new x whose covariance matrix is diagonal. Now, if a covariance matrix is diagonal, what does that mean?
Uncorrelated.
It means that the elements of the vector are uncorrelated. So, and if it's Gaussian and the elements are uncorrelated, what does that mean? They're independent, right? If they're uncorrelated and zero mean and it's Gaussian, then they're independent, right? Well, right. Okay, so what we have then is that x here, so let me draw a picture, okay? So we start with x, we put it into transform E transpose, and we get out x tilde. Over here the covariance is R, and over here the covariance is lambda, and lambda is as a diagonal matrix, and the diagonal elements are the variances of each component. So the picture is like this. You start off, if you looked at the probability distribution, P of x is equal to 1 over z times the exponential of minus 1/2 x transpose Rx. So if you look at this thing, and you set a contour surface. So let's say if this quantity as this quantity gets larger, then the probability density gets smaller. So if you ask for all values of x, okay, x of t are x less than or equal to some value, I don't know, let's just say 1, okay? That's a nice round number. That's essentially one standard deviation. Is a way of thinking about it. Then you get a contour, and does anybody know what the shape of this contour is? So I'll hold on that because nobody knows. So we'll derive it. Actually, in high school algebra, I think you did this, okay? But you've forgotten it. So x tilde here is equal to E transpose x, but that's an orthonormal transform, so I can take its inverse. So x is equal to E times x tilde, right? So over here, the probability density is P of x is equal to 1 over z. I'll put a prime there because that's a different z. Exponential of minus 1/2 x transpose lambda x, right? Now, here, x transpose lambda x, lambda inverse x. Oh, I'm sorry. This is an inverse. I left the inverses out. That was bad. Okay. Lambda x is less than or equal to 1. Okay. What does this mean? This means that the sum over, say, p of xp squared times lambda p is less than or equal to 1. That's just the way of writing it down in scalar notation. So if you have that the sum of the squares is equal, if you have an equation, nobody remembers what equation this looks like?
An ellipse.
It's an ellipse. Like that. That's a pretty crummy ellipse, okay? It's supposed to be aligned with the axes. All right. Now, let's say this is the two-dimensional case. P equals 2, right? So there'll be two eigenvalues. So you'll have, say, lambda 1 and then lambda 2, right? Now, there's two possibilities. One is that the lambdas are equal, and the other one is that they're not equal. If the two lambdas are equal, then you basically have an equation which is like x1 squared plus x2 squared equals 1. So what's that equation for? Circle, right? Now, if one of these, so this is like x1 and this is x2, right? Oh, x tilde 1 and x tilde 2. There's tildes on here. I got to put little tildes here. If x1 is 0, then the constraint is only that x2 times lambda 2, x2 squared times lambda 2 equals 1, right? So this point here is going to be the square root of lambda 2, right? And that point there is the square root of lambda 1, right? So the square root of the eigenvalues tells you the standard deviation. Oh, I keep saying the wrong thing, and you guys let me do it. What did I just say that's wrong here? There's an inverse here. So I have to take 1 over the square root, okay? Right, so, hold on. No, that's got to be right. Lambda, no, that's correct. I had it right the first time. So this is, I'm getting this mixed up. There's a divide there, okay? So the equation here, let me just write on another piece of paper so I don't get this all mixed up. Okay, so I have, say, x1 tilde squared over lambda 1 plus x tilde 2 squared over lambda 2 equals 1. That's the equation, right? So if x1 tilde equals 0, then I'm looking at the intercept with the x2 axis. Then I get the equation x2 tilde squared over lambda 2 equals 1, which implies that x tilde 2 squared equals the square root of lambda 2. Okay? All right. So those are the two axes. Okay. So that intersection right there is the square root of lambda 1, and this is the square root of lambda 2. So the eigenvalues of this covariance matrix R determine the intersections of the ellipse. If one eigenvalue is very large and the other eigenvalue is very small, then the ellipse is thin and long. Okay? Now, the transform in this direction, in that direction, the transform is x equals e x tilde. This is an orthonormal rotation, and without loss of generality, its determinant is 1. Okay? So it's a rigid body translation of this object without any reflection. If the determinant could also be -1, in which case you'd have a reflection, like a mirror reflection. When you look at yourself in the mirror, the person you see in the mirror is not a rigid body transform of you. It's a rigid body. It's an orthonormal transform with a determinant of -1, which is why you get all confused in that question I asked you, because you're flipped inside out. That's why, and your interpretation is that you're flipped left to right because your brain cognitively has to map it to something that you can understand in the physical world. Okay, but the mapping has a determinant of -1, which is what throws you all off. Okay. But, okay, this is the orthonormal transform with a mapping of 1, so there's no flipping, okay? So what happens is that, I'll just draw a general case. In a general case, the ellipse gets rotated, okay? What happens when you rotate an ellipse? It's not a very deep question, actually, okay? So this is an ellipse. It looks like this, right? What happens when you rotate it? Well, it looks like a rotated ellipse, okay? It's like that. It's only so complicated, right? And there's only so much you can do here. Your rotated ellipse, it's not that very it seems really simple in 2 dimensions, but if you go up to 1,000 dimensions, now the ellipse can get really complicated because there's a lot of ways you can rotate it. Okay, so you have a rotated ellipse, okay? Now, this axis here, that distance, that's lambda 2, say, and this is lambda 1, but there's some angle.
Square root.
Square root. Yes, thank you. Thank goodness there's students in here to correct me. Okay, so you're going to have some rotation of the ellipse. It's a rigid body rotation, so the ellipse doesn't get any bigger or smaller. It just rotates. And this distance here becomes the square root of lambda 2, and this is the square root of lambda 1, right? This way and this way. These are called the principal components, okay? The principal this is the principal eigenvalue because it's the largest eigenvalue. And these vectors here, when they're normalized to unit length, are the eigenvectors. So this thing here, that's E2, and this is E1, but unnormalized. Okay? So the intuition behind this is really clear. When you have a Gaussian random, multivariate Gaussian random vector, if you did a scatter plot of the distribution of the points, they would form a cloud which is an ellipse. The ellipse is like a football. It's in the United States, football is different than it is in Europe and in most of the world. But since we're always right, okay, our footballs are the correct ones, okay? Our footballs kind of look like this, just in case you haven't seen it. Okay, that's what the football. Other people's footballs, which would be basically the rest of the world, look like that, okay? But that's okay. So here, when I say football, I mean that kind of football, okay? So anyway, so they're like footballs, okay? And they rotate, and hold on, where was I? Okay, so yeah, so and the length of the square root, the length of the axes of the football squared represent the eigenvalues, right? And the directions represent the eigenvectors, okay? Now, and when you use the transformation formed by the orthonormal eigenvectors, and you apply it, you decorrelate them, you're taking the football and you're orienting it along the axes. So here, the thing's never correlated. See, there's no correlation between, if I have a scatter plot, right? If I have a scatter plot, and say the scatter plot looks like this, zero mean. So this is like number of cigarettes smoked, and this is rate of lung cancer, okay? You'd say, well, there's a positive correlation between those, right? And that's because it forms an ellipse like this, right? But if you rotate it with an orthonormal rotation, you can decorrelate it, right? So it's interesting. So let's say you have an image here. I'm trying to give you a little intuition into this. And these are 2 pixels, right? Now guess what? Nearby pixels in an image are correlated. So if you did a scatter plot of nearby pixels in an image, it would look like something like this. And the correlations, well, I mean, what'll end up happening is that, by symmetry, this is going to be at 45 degrees. Right? So what's the actual rotation you almost know what the orthonormal transform has to be that will decorrelate a pair of pixels. We can write it down right here. It's got to be 45 degrees, right? By symmetry. Okay, so assuming it's a stationary random field. So what will happen is this axis is formed by, this will be this one, this is pixel x1, and this is x2, right? So this will have to be x1 plus x2, but the problem is that would be unnormalized, so you have to normalize it, so you divide by the square root of 2. So this will be 1 over the square root of 2, 1 over the square root of 2, okay? And this will be 1 over the square root of 2 minus 1 over the square root of 2. So basically, this is equal to 1 over the square root of 2 times a matrix which is 1, 1, 1, minus 1. So that is the orthonormal transform. That is the eigentransform for decorrelating a pair of pixels. And now the eigenvalues then you get here, this will be lambda, I guess we're going to call that lambda 1. Actually, that's kind of a little weird. I should have called it lambda 2. And this is lambda 1, okay? And this is square root, square root. So the interpretation of this is that when you apply this transform, this will be the difference. This will be the sum of the pixels, and this will be the difference of the pixels, right? So the difference here, sigma squared difference is equal to lambda 2, or I guess we better call these lambda 1 or I'll really confuse you. Lambda 1, and this is sigma squared sum is equal to lambda 2, right? So this is the variance of the sum and the differences of the pixels. But now these are decorrelated. There's an interesting result of that, which is that whenever you have independent random variables with the same variance that are correlated, okay, then the decorrelating transform is always to take their sum and their difference, which is quite. I always find it to be very surprising that that's true every time I relearn it. This sum difference operator is very basic, and it's interesting. They only discovered in recent years in modern plumbing techniques this fundamental result, because when you go to take a shower, you know how you have the little thing here? Like it used to be you had the hot and the cold water and you could never get it right. But now they have like a sum and a difference. So you control the volume of the water and the temperature, right? And it's much better. So that's basically the same thing. Okay, anyway. So this is a very beautiful thing, because once you have, if you have x and it's distributed as it's normal with mean 0 and covariance r, okay, then and R here is equal to E lambda E transpose, then these are the eigenvectors. They're the fundamental bases on which the random process kind of has its unique behaviors. And each of these diagonal elements represents the variance along that axis, okay? So then you get X transpose is equal to E X tilde equals E transpose X. This is a decorrelating transform. So if you want to generate random these random vectors, it's very easy to do, because what you can do is this. You can say, okay, to generate sample from X, there's two steps. Okay, one, you generate, I'll call it, I don't know, Y to be normal with mean 0 and identity matrix. So what you just do is, so Xi is just normal with mean 0 and variance 1. And then you make them independent. So you use a pseudo-number generator in the computer to generate a sequence of independent Gaussian random variables with mean 0 and variance 1. And you populate a vector with p entries in it. Okay? That's easy enough, correct? It's like white noise, basically, you put in a vector, right? Then what you do is you do this. You say, okay, then 2 is first you take Y, and then you have to scale each entry appropriately. So what you do is you multiply it by lambda, the square root of lambda. Lambda is, now, if you tell me to take the square root of a matrix, I'll get very angry at you, because, like, in general, that's not entirely clear how to do. But for a diagonal matrix, that's fine, because there's a unique way to you just take the square root of the individual elements. Okay? So you take the square root of it, you multiply it by Y. That's going to scale each element by the appropriate standard deviation, which is the square root of the variance. And then what you do is you multiply by, let me make sure I write the right thing down, because if I wrote the wrong thing down at this time, it would be horrific. Hold on. Where's my diagram? Oh, here we go. Okay. So you multiply by E, and then that will be X. So what's really happening here is that this thing here is X tilde, right? So it's like you're taking X, right, is equal to the sum from I equals 1 to P of EI, because EI is the ith column of E, it's the ith eigenvector, and you're multiplying it by the square root of lambda I times yi, where this is IID. IID means independent and identically distributed, N0, 1. Okay? So while you're generating this ellipse in this space is you have axes. These are your principal component axes, right? This is E1, this is E2, and then you multiply it by lambda 2 and the square root of lambda 1 to scale it, because the length is different, right? And then the amount of variation, what you do is you use a random variable to decide where a Gaussian random variable with mean 0 and variance 1 to decide where you are on this line. Chunk, chunk, and then that becomes your point. So that's how the cloud is made in the multidimensional space. I didn't draw that too well, but you get the idea. Okay. Okay, now, so what happens is this. what you'd like to do is, you can use this technique to analyze high-dimensional objects. So let X be an image. So what you do is X now is equal to X1 through Xn. So these are all the pixels in an image, in any order you choose to put them in. And now you'd say, well, what I want to do is I want to, I can form the following thing. I can say, okay, hold on for a second. I don't want to stray too far from my nose. Okay, so what I can do is this. I'm sorry, I make that XP, okay? Now, what I can do is this. I can say, okay, I'm going to take X. Oh gosh, my notation here is a little messed up. Okay, and I'm going to have, this is X1, and this is Xn. And so these are n images. Right? So each of these is a column of the matrix. And each column of the matrix is an image. You form the image by putting the pixels in raster order. So this is going to be a P by N matrix. So it's a matrix of images. Normally what will happen is that this matrix is tall and thin, because you'll have a lot fewer images than you will have pixels. So you might have like 1,000,000 pixels, but you might only have 10 images or 100 images. But it's a lot taller. It's a tall, thin matrix. Right? Now, using that notation, then if we take X times X transpose, and we divide that by N, that's equal to S. This thing here is called the sample covariance. Okay, the reason it's the sample covariance is because it's not the covariance. The sample covariance is not the covariance, okay? Or one reason it's the sample covariance. A shoe is also not the covariance. So there's lots of things that fall into the category of not being the covariance. But this is special among them because it's the sample covariance, okay? Now, it has the particular property that the expected value of S is equal to R. I'll let you show that. But basically, if I take one, you see, one way of looking at this is that S here is really the same as 1 over N times, you can show it's the sum from N equals 1 to N of Xn, Xn transpose. See, this thing here, so the other way of looking at it is like this. This is a tall, thin, this is actually a column vector of width 1, okay? And this is Xn. And then this is Xn transpose. So that's sometimes referred to as an outer product. And each element of that matrix then is the corresponding product of the corresponding elements, okay? So so if you look at Sij, it's really equal to 1 over N times the sum from N equals 1 to N of, this is Xn I times Xn J. So you're taking the ijth elements, the ijth pixels of the nth image, and you're taking their products and you're averaging them. So this is like the sample correlation between those two pixels. Okay? This is maybe getting a little bit. Hold on, we're getting somewhere on this. Okay? So what you'd like to do is so S here, remember, is approximately equal to R. This is our S, this is the sample covariance, and R is the true covariance. We never really, typically we won't know what the true covariance is, because if somebody gives you some data, like say they give you a few images, you don't actually, you don't know what, well first of all, is an image a random process? No, okay? Okay, just wanted to reinforce that, okay? Because an image is just an image, okay? But we can model it as a random process. So S here is actually something we calculated from the image. Now, if the image were a random process, S would then be what? A random variable. It's actually a random matrix, okay? Because it's a function of random variables. Of course, the image isn't really a random variable, but if we model the image as a random variable, then we're modeling S as a random matrix. Is R, the covariance, random? The covariance is not random, okay? Because the covariance is the expectation of something. The expectation isn't random. The covariance is a parameter. It's deterministic, okay? So this is random, that's deterministic. This is modeled as random, that's modeled as deterministic. So since they can't be equal, because a deterministic quantity can't be equal to a random quantity unless the random quantity is almost surely equal to a constant, okay? So you know, in general, you wouldn't expect these to be equal, right? But it's the case. But the R is equal to the expected value of S. So therefore, you expect that S should be, as n gets large, you average a lot of images, the sample covariance should approach the true covariance. So in the limit, as n goes to infinity, S of S, that should equal R, and that would be by the law of large numbers. Because the law of large numbers, and there are various flavors of the law of large numbers. There's the strong and the weak law of large numbers. Says that the limit, as you take enough independent samples of something, should converge to its mean value. So this is the mean value of that. So it should converge to it in some sense, either in probability or almost surely. Okay. So now. Okay. So what we might want to do is compute the Eigen decomposition of S. So we get S equals E lambda E transpose. And this should be an estimate of Eigen transform Eigen value, right? So, okay, the problem is this. S is huge. S is huge because if P is large, S is P by P. So if it's 1 million pixels in the image, it's 1 million by million. So 1 million squared is what? 10 to the 12. Okay, so hold on for a second. So 1 million is 1 million. Then that's 1 billion. So it's 1 trillion. So it's a gigabyte. Okay, so times, if it's 8 bytes per float, or let's use doubles in MATLAB. So it's 8 bytes per double, right? So it'd be 8 gigabytes to store this for a 1 million by 1 million image. So, and then what you have to do is you have to do singular value. You have to do Eigen decomposition to find this. Okay, so that's a mess. Okay, you don't want to have to do that. That's horrible. Okay, so instead, there's a trick. What you can do is you can take X, and you can compute X now is a tall, thin matrix. You can compute its singular value decomposition. U, and now this is sigma, and this is V transpose. So this is SVD, singular value decomposition. The SVD is very important. Actually, in my opinion, and this is like heresy, okay, I could get in real trouble for saying this on TV. I think the SVD is more important than eigenvector decomposition, right? Because eigenvector decomposition gets all messed up when you try to have non-symmetric matrices. But SVD always works smoothly, okay? And for the case of symmetric matrices, the SVD and the eigen decomposition are essentially equivalent. So what happens is this: if you take the SVD, so you have X equals U sigma V transpose, and oh, by the way, so this is these are orthonormal columns. Orthonormal columns. These are orthonormal rows. Oh, in this particular case, we're assuming here that the thing is tall and thin, so then this is just orthonormal. This is a little bit specialized to the particular example I'm giving you. It's not a completely general interpretation of the SVD. And this is diagonal, because the SVD works for matrices which are tall, thin, square, or fat and wide. Okay. So so you have this. So then what ends up happening is that if you take X transpose, that's equal to U sigma V transpose, then this becomes V sigma transpose of sigma, and this is U transpose, right? So this then is equal to U sigma squared U transpose. So what this tells you is that sigma squared equals lambda, and U equals E. So for this matrix here, the eigen decomposition would be E lambda E transpose. U is going to be the eigen decomposition, eigen transform, and lambda is computed by sigma squared. So, but the singular value decomposition is a lot easier to compute, because what you can do is this. Okay, what you really want is you want the eigenvectors and eigenvalues of XX transpose, because now these E's will represent the basis vectors that represent the fundamental behaviors in the image. So these are the columns of E. These are columns are called Eigen Images. And you guys did the lab, so you know what that means, right? You've actually visualized this. The trick is, okay, so the singular value decomposition can be done very easily, because you can do a little trick, which is you can take X transpose X instead of XX transpose. This now, instead of being P by P, is N by N. You compute the eigen decomposition of this thing. So the eigen decomposition of this thing is going to be V, say, lambda V transpose. And once you have this eigen decomposition, now you can compute the singular vectors easily. Okay, so I just have to make sure I do this correctly. So yeah, to compute, then what you do is you say, okay, well, I know that then X is equal to U sigma V transpose, right? So I have, okay, so I have lambda and V. Oops, and V. So I have I perform eigen decomp on X transpose X. When I perform eigen decomp on X transpose X, I get V lambda V transpose. Okay. So then I have this, and I'm running out of time. I guess I'll just have to fix it up next time, but I'm almost close, okay? Because then Well, I won't try to finish it. I'll finish it up next time. But I'm almost done, okay? All right, good. So thanks a lot, and I'll see you next time. Thanks, bye.